that it seems easy when we do it together in class, but you're going to want to spend some time with it on your own. All right, so describe the end behavior. Okay, we're good at this. Most of us did really well on the quiz for this. So what do we need to do? Well, we need to recognize that this is a logarithm. And so with a logarithm, my normal end behavior is going to change. This would be my normal end behavior. But that's going to change. That notation is going to have to change. How is it going to change? Well, let's look at what it looks like. What does that do? That moves you 2 units to the left. So whatever's happening, I am not going to be able to go all the way to negative infinity. I'm going to get stopped at -2 on the right side. When I draw this, I'm either going to go up or down. I'm coming this way, okay. Now, which way am I going? Well, a normal logarithm, that guy right there is bigger than 1, so it's normal, or we call it normal logarithm. So it would go like this. But because I put that coefficient in front, it's going to flip it. So it's actually going to look like this. Would everyone agree with that? So, as I go to the right, I'm going down. And as I go to the left, this way, toward the asymptote, I'm going up. Is everybody okay with that? All right, what about this one? Now, this is an exponential. So it is going to have the normal end behavior. We're not going to change our end behavior. What is it going to look like? Well, be careful. That exponent is negative, and I do not want it to be negative. So I can make it positive by doing what? Flipping the base. So isn't this the same as 5/3 times 5/3 to the x? Now that's bigger than 1. That's positive. Isn't this a normal exponential then? So as I go to the right, I am going up. And as I go to the left, we're in my favorite sweatshirt again. Good job. Someday I'm going to have to put a bonus point in your column. As I'm going to the left, what's happening? I'm getting closer to 0 from the top. Here we go. Well, back in the day, 1977 to 1981, it was called Tri-State University, and that's where I went. My husband's a Tri-State engineer, which currently Tri-State's ranked above Purdue in engineering. Everybody's like, Tri-State, I don't know, Tri-State. You're right, there's no like name recognition. It's not like going to Stanford or something. But I'll tell you what, I got a great education there. Got a great education.
Do you know Mr. Passwater?
I have no idea, but I'm sure it wasn't Tri-State.
I'll say Amos Purdue.
I don't know. It's pretty bad. We've not gotten that close to talk about that stuff. As a junior and a senior in my majors, which were math and English, so in my major subjects, oh gosh, I can't remember now, but my classes were under 10. I mean, they were small. They were small. Because Tri-State was small. All right, describe the rate of change of these two functions. All right, describe the rate of change of these two functions. So I'm looking for two words. First of all, positive or negative. What's happening here? Negative. Why is the rate of change negative? Because the curve is going down. This rate of change is positive. All right, now I want increasing or decreasing. Not the function itself, but the rate of change. What do I look at if I want to know about the rate of change? Concavity. Bingo, good job, concavity. So this is concave up. So the rate of change is increasing. Now make sure you're clear in your notes. These are, I'm talking about the rate of change here. I'm not talking about the curve itself. This curve is decreasing. Okay? That's why the slope is negative. But the rate of change is increasing. All right, how about this guy? What's happening over here? Also increasing. So the rate of change is increasing because the curve is concave up. Exponentials and logarithms are either concave up or down. So they're always either going to be, the rate of change is going to be increasing or decreasing the whole time. All right, which are equivalent statements? All right, take a second, look at all those, and see if you can figure out which, if any of those are equal to each other. So we have to do some base manipulation. What'd you get for that one? The first one? 3 to what power? Yeah, 1 plus 4x or 4x plus 1. Because this is 3 squared to the 2x, and that's 3 to the first. So I'm adding those exponents. All right, what'd you get for the second one? Isn't that 3 to the 6x? Folks? Yes? 3 times 81 to the x. So that's 3 to the first times 3 to the 4x. What am I going to do with those exponents? Isn't that going to match this one? All right, let's see what else we've got. 243 to the x. That's 3 to the 5th. 3 to the 5x. How about 3 times 3 to the 4x? Yeah, isn't that another one? That's 3 to the 1 plus So 4x plus 1. So that matches that and that. Alright, what do I got next? 3 to the 5x, that matches something. So that one matches this one. And the last one matches, so there's, how many in boxes? 4? And then she circled them that match each other. Are we all right with that? Okay. Now what we need to do is go to the review sheet that Julian handed out, and that was the one in my handwriting that's all cut and pasted together. And we're going back to the back. We'll start at the back and work up backwards, because the sheet that we just finished, and didn't quite finish, references problem 17 on here. So we're gonna do 18, and then we'll do 17, and then we'll finish that, all right? So 18 is easy. Which of the following could represent the data in a semi-log plot where the vertical axis is logarithmically scaled? You can automatically rule out C and D. Would you agree with me? Yeah. They are not logarithmically scaled. I need the point 10, 30 to be on the graph, so 10, 30 looks like that would be graph A. A is your answer. Amen. Right? Okay, now let's look at 17. 17 continues on to this other page. There's lots of questions about 17. American Cell Service. X represents, so X is 1. Okay, so pay attention to that. When you enter this data, you're not entering 1999, you're entering 1. And use logarithmic regression to fit a model, and then we'll use the model. Okay, so let's go ahead and do that. 1995 is 1. It says, look at the read it. Read part A. Go in order, right? There's no skips. Oh my gosh, I can't believe I just did that. I'm such a, I'm gonna need help because I gotta start all over again. You just do it for me, you'll just tell me what the answers are. All right, go ahead. I totally messed up, so you need to go ahead and see if you can answer the questions. Emergency.
I got my question.
All right,
Yeah, I just usually do like second count. Increase the
Back in the good old days, back in my day, no one had phones. Only 12.69%. Bro, me and my BlackBerry are way back.
Yeah.
I'm like a type it out. My iPod. I want an iPod. Either one of those.
all right, I don't know, I messed around here. I got, for my equation, it actually looks like it's pretty good, because my R value is pretty good. I got a 12.7038 plus 28.52. You're laughing, is this wrong?
Did you get them? That's a different number.
That's right.
That is what I got. Yes.
Not quite.
It's right.
Come on, sorry guys, plug and chug.
Somebody can get that.
I got it, Mrs. Ford.
So what, if you are like close but off a little bit, what happened was you got you got a wrong data point in there somewhere. So check your L1. You did logarithmic, right?
I did linear.
Oh no, we're still on this one. We're still on this one. Use logarithmic regression. Yeah, we're on the actual sheet that has column 17 on it. So this is the logarithmic regression. So I am doing 17A. All right. Now when I go back to that other sheet, it's gonna have me do a linear regression, which I'll do that later. Data's in, that'll be easy. But right now I'm doing this one. And then it says use the model to determine the percentages in 2013. All right? So if I'm doing 2013, then my X is gonna be 19. So I'm gonna put in Y, parentheses, 19. Did you get 96 point, basically 680? Remember, you could also plug in 19 right here. But if you do it the way I did it with the stored equation, we don't have any round off. This way you're gonna have a little round off that may or may not throw something off, I don't know. But it's better to use your stored equation if you can. All right, are we okay with 17? All right, let's go back to that other page then, where it said number 9 was, of course, number 17, find the residual value for 2000. All right, now you got 2 options. Super simple and easy. All right, what's the super simple option? Use the residual column in the calculator. So 2000 is what, the 6th data point? So I'm gonna go to stat, edit, and I'm gonna go over to the residual column, And the sixth entry is negative 0.0051.
I got negative 7.177. It's in the sixth one.
Make sure I count it down. Yeah.
So I got, this is the sixth one. I got what you got for the equation part.
Yeah, you're in the second.
What? I told you this calculator is wacky. Second. It should say reciprocal. Wait, second is that?
Do I have to, maybe I have to redo the residual?
My calculator is.
Okay, did anybody else get this number?
Yeah.
Okay, I'm trying to figure out why his isn't.
I'm trying to use the I'm like an old man. It's like grandpa.
There's no way.
My grandson.
Okay. What does this mean? What does that residual mean? Negative 0.0051. What does that mean?
Overestimated.
Remember that your residual, I did it the super simple way, my calculator already has it down, I did it. But if you were gonna do it the other way, a residual is the actual minus the predicted. So if that comes out negative, that means the predicted value, that is the one that came from the formula, is too high, right? A little bit. In this case, it's close, but it's a little bit too big. All right? So if you can't get it from your residual column, you can always do actual minus predicted. So if you have an actual value, 63.8, you could get a predicted value by putting in 6 here and then subtracting them, if you needed to do it by hand, okay? Find a linear regression for the data. Well, that's easy because you've already got the data in. So go to Stat Calc and do a linear. And it's A plus BX. And this is probably what you had before, see? Did you get y equals 32.355 plus 4.002x? So that's a linear regression for the data. And then it says, find the percentage of Americans with cell phones in 2013. In 2013, oh yeah, that's, I need to plug that in, so get my Y. And 19, that's the 19. Did you get 108.386? Okay, we have a problem because the unit on that would be percent. So that would mean that 108% of the people have cell phones, and obviously that doesn't make any sense. So, kind of look at the situation This data, I think, just feels more logarithmic than linear, because what does linear mean? It's going up basically by the same rate every year. Well, what's happening? In the beginning, when cell phones first came out, what happened? More and more people got them, so the increase year to year was bigger. But then what happens, as more and more people have them, the increase starts leveling off. And isn't that a logarithmic curve? When it grows, and then levels off? This is not linear data, because linear data will just keep going. And that doesn't make sense in this problem. Right? Okay. All right, let's continue going backwards. Oh, shoot. Let's quickly do number 16. We can do it. We can do it. We're finding the inverse. We know how to do that. So I switched my variables right off the bat, as I'm sure you did. Now I'm going to get this by itself, so I'm going to subtract 1 and divide by 3. In that order, guys, that's the way we solve equations. So we're going to subtract the 1 and divide by 3. And then loop-de-loo it. So 7 to the x minus 1 over 3 equals y minus 3. And add 3. So 7 to the x minus 1 over 3 plus 3 equals f inverse. Yep. I told you we could get that done. That was just a minute. All right, let's wait quietly. We're not getting our phones. We're not doing anything. We are waiting quietly for prayer.